All right, everyone. There's a lot going on in this class, so we're going to go through bit by bit. I know there's a lot you have to turn in. You might need a separate piece of paper, so please grab one if you don't have it. So let's see what we're doing here. Our goal is to determine how mass, speed, and radius affects centripetal acceleration and centripetal force. We're going to introduce a thing called factor of change. So our centripetal acceleration equation is right here. Centripetal acceleration is equal to v squared over r. Now, keep in mind that's the tangential velocity or speed, because remember, it's always changing in direction. So it's the magnitude of that number. It's really similar to like our acceleration equation, change in velocity over time, but this is centripetal, so it's v squared over r. If you want to check it out, the units actually end up being the same. They're still meters per second squared. Now, centripetal force is simply the mass times the centripetal acceleration. So it's mv squared over r. You might see written both ways. Just be aware of that. I would just, memorize all these. They are on the reference table, but I would just make sure you know all of them. Now, how do we use these? Well, remember, centripetal force is the sum of all the forces pointing in and out of the circle that result in something moving in a curved or circular path. So just like before, we'd sum of the forces equal ma. Well, now it's the sum of the forces, some of these centripetal forces, if you will, equal mass times centripetal acceleration. All right. So I really want to emphasize that this unit is just like the last one. And I wouldn't think of it as, oh, I have to remember everything I did last unit. I would think of this as, well, now I'm just going to apply those things in a new way that will make you even better at the previous topics and will help you a lot in learning this topic. Don't get caught up with the fact that it's moving in a circle. What we're doing is really no different. So give this question a quick read and then I'll do it. So it's saying when the speed is changed from v naught to 2v naught, what is the new centripetal acceleration in terms of a naught? Well, my equation is a naught equals v naught squared over r. I can make it a capital R, but it doesn't really matter. So what we're going to do right now is called factor of change. Now, please make sure you actually use this method. This is an easy example, but later on in the year, because we're going to do this all year, you need to use this method. So please make the choice now to use it for these easy questions, and it will make your life so much easier later on in the year. This is a very powerful tool. You can use it in pretty much any equation you will ever use in your life. I can't emphasize enough how important this skill is that we're about to do. So factor of change is very simple. You basically want to see how changing one variable will change the others. So we have an equation for centripetal acceleration. A naught is equal to v naught squared over r. What we're going to do is we're going to see what's our new centripetal acceleration if I double v naught. So I'm going to call that a naught prime. Then I just rewrite the equation, but I replace each variable with the factor by which it's changing. So if you are doubling it, you put in a 2. If you're tripling it, you put in a 3. If you're cutting it in half, you put in a 1. Or excuse me, a 1/2. If you're not changing it, you put in a 1. So I'm going to replace v naught now with 2. But I'm still squaring it. That's very important. And I replace r with 1 because it's not changing. So I get 4. Now my answer is not 4. My answer is 4 times my original value. So my answer is actually 4 a naught. So by doubling the velocity, I quadrupled my centripetal acceleration, which you can kind of see in this equation because it's v naught squared. Now, again, this is an easy example. It's going to get a little bit more complex as the year goes on. So try this next one on your own, then I'll do it here. So a naught prime equals, well, now I'm tripling the velocity here. So I replace v naught with 3 and it's squared over 1. So I get 9. But again, my answer is not 9. It's 9 times my original. So 9 times a naught. So now it's asking about what happens with t. Okay, now first off, I really like this free body diagram. You'll notice this is a top-down view of the object going in a circle. So it would be very hard to draw the normal force and the force of gravity here. So this is a side view, so we're looking at the circle from the side. The tension points towards the middle of the circle, and the normal force and gravity point up and down. So the circle is kind of like this. It's like a very flat circle because we're just looking from the side. This is a side view. Notice how the normal force and gravity point cancel out. So if it says anything about net force in one of these, well, you know those two forces cancel out. So how would we do this? Well, we should start with, you're probably saying, how does tension work in here? We'll start with the sum of the centripetal forces equal m v squared over r. Now the sum of my centripetal forces, well, in the original equation, there's only tension. There is no other force that points in or out of the circle. So tension is equal to m v naught squared over capital R. So in one of the cases, I am doubling v. So I'll call that t prime. The mass doesn't change, so I put in a 1. V naught is doubling, so I put in a 2. Don't forget to square it. And r is not changing. So t prime, I end up getting 4t. So that'll be this choice here. Now when I triple the velocity, the velocity, t prime equals 1, 3 squared over 1, because the only thing that's changing is v. So I get 9t. That'd be choice D. Now I could do this with any of the variables, but for now with this specific question, it was focusing on v. So try this one on your own, then I'll go through it. So just pause the video and try it on your own. The two keys here, the ratio of the speeds, v4 to v1 is 2, and r4 to r1 is b, as in boy. Well, how does that work out? Well, let's check this out. So if I write an equation for f1, that's equal to m v squared over r. The two runners have the same mass, but the radius and the velocities are different. So how does f4 compare to f1? Well, f4, the masses are the same, so I put in a 1. But by what factor is the velocity changing? v4 to v1 is 2. So this is twice as big. And the radii, how are those changing? Well, r4 is b times as big. So I get 4 over b. So that's where I get this one. f4 is equal to 4 over b times f1. This question is way harder if you did not use the factor of change method. With factor of change, this is a pretty easy question. It's just interpreting what the factors of change actually are. So this one might seem complicated, but overall it's not too bad. You just have to draw a little picture of what's going on here. So there's a lot of planet stuff in this unit. We're not really there yet, but here's a planet and here's the moon. You don't really need to know the planet stuff to answer this. So the only force acting on the moon right now is the planet, is the force of gravity to the planet. So in this case, that is the agent of the centripetal force. So the centripetal force, sum of the forces, equal m AC. Now, why did I not plug in v squared over r there? Because I'm looking for AC, so why plug in v squared over r? So the only force pointing in or out of the circle here is Fg. So that's my only force there. That's equal to m times AC. Now you plug in Fg that you're given there and you plug in the mass, you should get a centripetal acceleration of about 20 meters per second squared. By the way, these are all in the progress check questions. So give this question a read. It's a little bit confusing. So this student's basically making this claim. They are saying that the tension provides the centripetal force, therefore the velocity should remain constant. Now, I don't know if it mentions anywhere that the tension is constant. But we have T equals mv squared over r. So the student is saying, well, the mass isn't changing, r isn't changing, and T isn't changing, so v should remain constant. The student's making one huge mistake, though. They are assuming that the tension is the only force that they need to consider, the only force that's pointing in or out of the circle. So I'm going to erase that. There's another force at play here. Whenever we discuss vertical circles, that's a dead giveaway that gravity is at play here, and you cannot ignore its effects. So rather than answer this question, I'm actually going to solve for the tension at all these different points just to show you why this question is a little bit more complex than the student is making it out to be. So we're going to go through A, B, C, and D. Now, I didn't leave you room to do this here, so you might have to get another piece of paper for this. So the radius is 1 meter, and the mass of the ball is 0.5 kilogram. So the weight of the ball, Fg, is 5 newtons. So please keep that in mind because I am going to use that repeatedly. So let's do A. A is at the top of the circle. So for A, we have tension pointing down, and we have 5 newtons pointing down. So the sum of the centripetal forces is equal to mv squared over r. So the two forces are going to be tension plus 5 newtons equals 0.5 kilogram. Or excuse me, 0.5 kilogram. Now V is going to be 3.16 squared. And that's 1. So let me grab a calculator here. So we have 3.16 times 3.16. I'm doing my phone calculator. So this is really interesting. I get that the tension here is 0. Now, why is that? Well, if you think about it for a moment, if you spin a ball around in a circle, if you spin it around really slowly, as slow as you can, you notice that the string kind of gets slack at the top when you spin it really slowly, like just at the point where it just makes it over the circle before the string collapses. So kind of interesting. Well, how would we do B now? So B, very similar. But B, you'll notice the free body diagram kind of looks like this. Tension points to the middle, and gravity points down. When I do the sum of the forces, I do not include the 5 newtons because it neither points in or out of the circle. Now, does that 5 newtons actually make this accelerate? Does it slow down? Yes. But I don't have to account for it in this equation. So this should just be T equals the mass. V is going to be 5.46 squared over 1. Let's do the math there. 5.46 times 5.46 times 0.5. And I get about 14.9. So the tension there is 14.9. I'm not going to do D. You can see how D works out to be the same. But try that out. And let's see C. C is interesting. Tension points up to the middle of the circle. Gravity points down. Sum of the centripetal forces equal mv squared over r. So here I have tension is positive plus a negative 5 now equals 0.5, 7.07 squared over 1. So I can't really do that math in my head, but 7.07 times 7.07, that's basically 50 times 0.5 plus 5. I get that the tension here is 30 newtons. So the answer to this one is no, because the centripetal force exerted on the ball is a combination of the tension and the force due to gravity. The student assumed that the tension was the only force responsible. But notice that the tension on its own is changing too. So a lot more is at play here. So when an object goes around a circle, its speed can certainly change, unless it says it's going around at a constant speed. So for these questions here, please try these on your own first, and then I will post the solutions to them, but please try them on your own first. Okay, so for 1, 2, 3, 4 pages here, try them on your own first. So for this one here, this is actually touching on some of the stuff you just did. So you should have just did that activity and checked out the solutions to it. If you watch this video here, you can find the video link and the PDF version of the notes. You can just click on it. But basically, it shows us a car skidding out, showing that friction is the agent of the centripetal force when a car goes in a circle, which is something we've spoken about before. So this is the entrance ramp to the Seaford Oyster Bay Expressway. I don't know if you could tell, but it makes actually a really good circle for most of it, except for the part where you get on and where you get off. So if you look at that car at the top there, let's draw the centripetal force and the velocity on that car. We'll do the centripetal acceleration too, why not? So the centripetal acceleration points to the middle. The centripetal force points to the middle. And the velocity is tangent to the circle. So using the video at the beginning, explain why friction is the agent of the centripetal force. Well, without friction, the car can't move in a circle. That's it. So the coefficient of static friction between rubber and asphalt is mu. Okay. So if you recall, our force of static friction equation is equal to the coefficient of static friction times the normal force. All right. So that is for only when, well, I should say less than or equal to, but they are only equal when you have the maximum amount of static friction. So with that in mind, let's try out this next part here. So we're going to solve for the maximum speed you can go around this curve in terms of mu, r, and physical constants. So the first thing I need to do is sketch a free body diagram of the car from behind. So I'm not going to draw the free body diagram as a dot from behind. Well, I know then that I have normal force pointing up, and I have gravity pointing down, and I have friction that keeps this in the circle. You should be able to tell here, without me going through it, that the normal force is equal to Fg. Therefore, the normal force is equal to mg. That was something we worked on a lot last unit. Well, how about this force of friction here? Well, in the circular direction, the sum of these centripetal forces, just change this color here, sum of the centripetal forces is equal to the mass of the object times the, well, v squared over r, because I'm looking for v max, so I know that I need v in there somewhere. The only force is going to be the force of friction. Which is equal to the coefficient of static friction, which is just coefficient. That's the normal force. And I know that the normal force is equal to mg here. So what I would end up with here for my speed is mu, is the square root of mu r g. So this is the maximum speed. Now, why is it the maximum speed? Because at max speed, the wheels are about to slip. That's a really important idea. The wheels are about to slip at that point. Therefore, you can use that the force of friction is equal to the coefficient times the normal force, because it's at that threshold point where the wheels are about to slip and you're about to lose control. So there's always a recommended speed around curves. Is that recommended speed Vmax? What do you think? Just throw down a number or throw down an idea. And for wet surfaces, the coefficient of friction is lower. So how would that affect Vmax? Well, I know Vmax, we just said, is equal to the coefficient GR. So think about how all these factors affect Vmax, excuse me. If mu goes down, what happens to Vmax? If R goes down, the radius of the circle, if the radius of the circle is smaller, so it's a tighter circle, how would Vmax change? If G goes down, if we were on another planet, how would this change? Now, here's a good food for thought question. Just read it really quickly, and then I'll go through the answer. Try it out on your own before you see my answer. So most turns are actually banked. Even if you do indoor track, a lot of the turns you run on are banked. Why is that? Well, if we think about the forces in this case, we have gravity pulls down. I should have just going to do this in different color so it's easier to see. Gravity goes down, Fg. The normal force goes this way. And friction goes this way. Now, why does friction go that way? Because it prevents the car from slipping to the outside of the circle. So think about why this actually helps the car. The reason it actually helps the car is because now the normal force, or at least a component of the normal force, points towards the middle of the circle, as well as a component of the force of friction. So now you have two forces that help it stay in the circle. And you might be saying to yourself, well, before the whole force of friction was pointing towards the middle of the circle. Now it's only in a small portion. But you realize that normal force is always going to be bigger than the force of friction, usually anyway. So what you end up getting is more centripetal force in total. All right, so that's where this comes from. Now, we don't really do banked curves in this class, but I just think it's a good thing to mention that by being on a banked curve, you have a component of your normal force points towards the middle of the circle. Therefore, it makes it a little bit easier for you to stay in the circle. All right. That's all I got. Make sure you take down the notes that I posted for this page here. All right. Or these pages. But try them out on your own first. All right. And make sure you submit everything